All right, well, let's get back to it. We have just a couple of more properties to discover, so let's see what we can do. First of all, I want us to recognize that, okay, so I've got x and y. That's the same as sine and cosine. So let's just stick that in wherever we can stick that in. Right, so our terminal point, x comma y, we can write as cosine comma sine. And actually, that's going to happen quite a bit in this class. We're going to have sine t, or cosine t comma sine t. And also, when we start moving into the world of angle measure, we'll start having cosine theta comma sine theta, which theta is just another number, but you'll see this come up as we move forward. So hold on to that. We can represent terminal points as cosine comma sine. And also, right, remembering our unit circle equation, x squared plus y squared equals 1. Well, x is cosine, so I've got cosine squared. Y was sine, so I've got sine squared equals 1. This is a fundamental, very important identity that we will be using rather almost excessively, like crazy amounts of use in this class. This is known as the Pythagorean identity. So-called because it kind of ties in with the Pythagorean theorem, and I'll show that when we get to triangle stuff. This actually is fundamental, very useful. Now, it's not going to be the case that cosine plus sine equals 1. It's not going to be the case that cosine plus sine quantity squared, so you add them and then square it. That's not going to be 1. Not always, not usually. But for any real number t, any number under the sun, no matter where you end up, if you take the x-coordinate and square it, take the y-coordinate and square it, you get 1. And equivalently, you take the cosine square it, take the sine square it, add it together, you're going to get 1. And now for a bit of a profoundly mathematical moment. I've got something that it's kind of useful. So the very first thing I want to do with it is rewrite it in as many different ways possible to try and see as many possible applications as I can. So this same thing can be rewritten two ways. Firstly, I can divide both sides by sine squared t, right? Whatever real number goes in for t, sine t has to be some real number out, so I can divide both sides by it. Unless, of course, sine is 0, in which case I have some complications, but it'll be okay, promise. So I can divide both sides by sine squared, so I'll have sine squared over sine squared, I'll have 1. Cosine squared over sine squared becomes cotangent squared, and 1 over sine squared, well, that's just cosecant squared. We do a similar thing, just dividing through by cosine squared, and I get a very similar looking identity. And these are all always true. But Mr. Terrell, you should protest. What if sine had been 0? Well, this is still true, actually, because I've got now undefined on the left and undefined on the right when sine is 0. And if I have this one and cosine happened to have been 0, well, I've got undefined on the left, undefined on the right. These equations are always true. And yes, false equals false is true. Let's not get into logic tables. It works out. So yeah, these are identities that we can always use. And later on the semester, we will use them quite strongly. So these are things that we can have and use and say about trigonometric functions. These how they relate. And while we're in the vein of relating functions to others, here's something that will be a little tough to swallow. I can write a function in terms of another function. And I've been doing that for a while, right? Tangent was sine over cosine. I just wrote one function in terms of another. Secant was 1 over cosine. I just wrote one function in terms of another. But it's actually the case that we can use the Pythagorean identities we just had to write any function in terms of, if not any other, pretty close to it. So suppose I had tangent of t for some terminal point after moving t ending up in the third quadrant. And I want to take that tangent of t, I want to write it exclusively in terms of secant. So the way I could do that is I take the tangent and secant Pythagorean identity. And then I solve for tangent in terms of secant. So the 1 gets subtracted off. I have secant squared minus 1. I take the square root of both sides. I got plus or minus root secant squared minus 1, which does not simplify to be plus or minus secant plus 1 or anything like that. Don't pretend. This does not simplify further. But since I am in the third quadrant, right, I assumed as much, that means tangent is positive. Right? Because if I'm in the third quadrant, sine is negative, cosine is negative, so that ratio is positive. So I keep only the positive root. So we just successfully wrote one trig function in terms of another. And sometimes that's to our advantage. In fact, and you're going to have to take me at my word for this for quite a while yet, trigonometric substitution, doing things like this, is something that happens as late as Calc 2. It is an integration technique, believe it or not. So it is something that you might want to hold on to. And one other property that I want us to look at is relating how we get a terminal point if we move clockwise versus counterclockwise. How can I relate those two terminal points? This is a concept known as even-odd identities. So here's my graph that I'll pull up here. Right, there's my unit circle. And so let's say I move some bit in either the counterclockwise positive direction or the clockwise negative direction. How do I relate the one point to the other? And we see no matter how far we move, no matter how far we rotate, the terminal points are related very clearly. The x-coordinates are the same, and the y-coordinates are mirrored opposite. So x equals x, and y is now negative y. Well, let's substitute back. If I go t versus negative t, I get the same x-coordinate. Therefore, there's a property. Cosine of negative t equals cosine t. Also, because your y-coordinates are mirrored opposite, negative t gives you negative sine t. These are two very simple properties about sine and cosine. So cosine is direction independent, I guess. If you start at starting position 1, 0 and rotate either clockwise or counterclockwise, you'll have the same x-coordinate, you'll have the same cosine value. Whereas for sine, you get almost the same thing. It's just now negative instead of being positive, or positive instead of having been negative. And then, of course, you take the tangent, which is the ratio of those two guys, and you find out that tangent is also, like sine, it is also odd. You get negative tangent t out if you put negative t in. So these are pretty useful as well. It's going to be the case, and actually fairly soon, it's going to be in the graphs of trigonometric functions. I'm going to show you a time where it is actually useful to pull out this negative from the argument. Obviously, it's immediately useful here, but it can also be useful here, and I'll show you that. And so here we are. We've got quite a few properties of trigonometric functions now. We know when they're defined, when they're undefined, when they're zero, when they're positive, when they're negative. So what happens as we move around the quadrants, and also what happens as we move around the quadrants in the opposite direction. We have these identities, the Pythagorean identities, and we can also write one function in terms of another using Pythagorean identities. So we've got quite a lot in terms of function behavior under our belt. Quite a lot that we have exposure to. So that's, I think, a good stopping place. Let me know what you might want me to talk about a little bit before the next class or at the start of the next class, and I will see you then. Have a good one.